So the three leading ideas to explain spiral structures are density wave theory, the self-sourced and self-sustained model, and the swing amplification model. So we're going to start with density wave theory. Yes. The oldest explanation we have for spiral structure, and it suggests that these spiral-shaped waves propagate through the galaxy in much the same way that a tsunami wave or a ripple passes through water. Now, the difference between this idea and the original idea that spiral galaxies rotate rigidly as one is that in the density wave theory, it's not the stars that are moving, it's the medium that the stars are moving through. So imagine if you have a wave passing through a crowd of people. People don't actually move, but the wave passes through them. In this case, it stays the gas and dust in the galaxy that forms the spiral-shaped waves that move through the galaxy. And as the waves pass through, they squeeze the gas and dust together, triggering the formation of new stars. So it s the fact that we can see all the young hot blue stars in the spiral arms. But as we saw earlier in this video, 70% of galaxies have spiral structure. But only half of those galaxies have the gas and dust and young stars in the spiral arms. This doesn't match up with density wave theory. A second prediction of density wave theory is that as you go from the center of a galaxy to the outskirts, the amplitude of the wave increases, meaning that you expect the spiral arms on the outskirts of a galaxy to be wider and larger than the ones close to the center of the galaxy. But observations of spiral galaxies tell us the opposite, that the spiral arms in the center are wider and larger than the ones on the outskirts. So density wave theory is struggling to explain what we observe in galaxies, which is part of why we've started to look into the other models. The next explanation is called the self-sourced, self-sustained model. And this model proposes that spiral structure grows bottom-up from small-scale structure, meaning that the stars and gas and dust in the galaxy clump together into smaller spirals or bubbles, and those small-scale features grow in size until we see these large-scale spiral structures. And in this model, the spirals live up to their name and are literal spiral shapes. In this model, each spiral shape is made up of both gas and stars, and it's the stars and gas that rotate around together to form these spiral shapes. One thing that this model does well is that it can reproduce a wide range of spiral shapes that we see in galaxies, including ones with 2 arms, 3 arms, 4 arms, ones that are too fluffy to count. It can even reproduce the rarer galaxies that don't appear to have any spiral structure at all. Because in this model, galaxies start off with a bunch of pre-existing clumps of stars. And if those clumps don't align in any particular direction, then you end up with a galaxy that looks like it should have spiral structure, but doesn't. The issue with this model is that we've never actually observed the smallest scales of spiral structure. We haven't directly observed these stars and gas forming these little tiny spirals or bubbles. Another problem with this model is that it breaks down when you want to talk about how spiral structure changes and evolves over time. We do know that spiral structure exists in young galaxies, but we also know that many galaxies are old and have had spiral structure for billions of years. So there needs to be a way to connect the two. So that's where the third model comes in, the swing amplification model. Now this is the model that I work on, and it proposes that spiral structure grows from these tiny, small-scale random motions that you see in galaxies. And the spiral structure emerges from those motions. And I've made a whole video about this already, so definitely go watch that after this one, if you want to hear more details about how it works. But I'm going to give you the elevator pitch version here. So in the swing amplification model, spiral structure starts out small, but it's not necessarily like a spiral. It's more like a ripple or a bubble. And the reason it's a bubble is because when stuff goes off in space like a supernova explosion or a black hole, eating, stuff that sends ripples out from that point, and those ripples stretch and distort the galaxy in slightly different ways. And that distortion has a unique pattern that is kind of spherical at first, but quickly breaks down into a thin pancake. This pancake then drifts around the galaxy, and as it drifts around, finds other ripples and other distortions caused by other random events. And as the pancake moves through those regions, it interacts with those ripples, and sometimes it winds up amplifying them, making them bigger, and sometimes it unwinds them, making them smaller. Over time, these pancakes travel all the way around the galaxy, and as they do, they keep interacting with other ripples, stretching and twisting them. This stretching and twisting means that sometimes the pancake itself stretches and twists, and eventually it settles into a shape that is elongated in one direction and wrapped around itself. creating a tightly wound spiral shape. Once you have this spiral shape, it's very stable, and it survives many rotations of the galaxy without changing shape. So this model is good at explaining how spiral structure can survive for billions of years. The key to this model is that it's emergent. This model is good at explaining how spiral structure can survive for billions of years. The key to this model is that it's emergent, meaning that it comes from the collective motion of a whole load of individual objects, the stars. In this model, each star is like a swinging around the galaxy, and the spiral shape emerges from all of those swings combined. This model is also good at explaining the winding problem, because as the pancakes drift around the galaxy, they collide with the edges of the axes. And that collision acts as a drag force, slowing them down and tightening the spirals up as they get to the edge of the galaxy. But there is still a lot that we don't know. All of these models have issues explaining what causes spiral structure in the first place. All of these models ignore the smallest scales of structure and the way that galaxies evolve over time, so there is still a lot more work to do. But I hope that this gives you a flavor for how scientists approach trying to explain the world. We start with an observation, in this case, spiral galaxies. All of these models ignore the smallest scales of structure and the way that galaxies evolve over time, so there is still a lot more work to do. But I hope that this gives you a flavor for how scientists approach trying to explain the world. We start with an observation, in this case, spiral galaxies. And we come up with a few different models to explain it. So there is still a lot more work to do. But I hope that this gives you a flavor for how scientists approach trying to explain the world. We start with an observation, in this case, spiral galaxies. And we come up with a few different models to explain it. We start with an observation, in this case, spiral galaxies. And we come up with a few different models to explain it. And then we try to rule out which of those models are incorrect by making predictions. And then we test those predictions with observations. And we repeat this process until we arrive at the best explanation we can have for the world. If you enjoyed this video and you want to hear more about the swim amplification model, then you can watch this video over here. Or if you want to hear more about dark matter, you can watch this video over here. If you enjoyed this video and you want to hear more about the swim amplification model, then you can watch this video over here. Or if you want to hear more about dark matter, you can watch this video over here. And you want to hear more about the swim amplification model, then you can watch this video over here. Or if you want to hear more about dark matter, you can watch this video over here. Thank you so much for watching, and I'll see you next time.